Okay. Um, let's talk about shapes of molecules. Okay. Shapes of molecules is based on one principle. Okay. Just go through the principle briefly. Let me show you. Okay. It's actually called electron repulsion theory. Okay. Electron repulsion theory. Let me see if I can show you. Is it? Molecules take up the shape that minimizes the repulsions between the bonding and the lone pair of electrons. Molecules take up the shape that minimizes the repulsion between the bonding and the lone pair. You will not make sense of this, not for now, okay? But when we start applying it, that's when you can make sense of the thing. Now back to the point. Now back to the next thing. The lone to lone pair electron have the strongest form of repulsion. I want to assume you understand what I mean by lone pair. If you have this situation in chemical combination like bonding, like covalent combination, if two electrons share this, if two elements shares this electron, and on this one there are two, there is something like this. Now this probably will be the structure of HCl, okay? HCl, for example. Now this one that is not taking part in chemical reaction is called lone pair, okay? Lone pair. The one that is taking part is chemical bonding is called the shared pair, okay? This is the lone pair. This is the shared pair. Shared pair. So what this diagram you see here is saying that the lone to lone pair has the strongest strength of repulsion. So what they're saying is that the repulsion between these will be greater than the repulsion between these. So in a literary sense, these two will push each other farther than this would push. That's the implication. So the next one is lone pair to bond pair to bond pair, like that. Okay. Now let's try to pick an imaginary structure and use that theory to explain it. My structure is like there's one element here, there's one element here, okay. There is, or rather, let me use a simple drawing. There is beryllium here. There is chlorine somewhere here. There is chlorine. Now I want to predict the shape that this would have. Okay, beryllium is in the electron configuration is 2,2, I think. Hydrogen, helium, lithium, beryllium. That's 4. That would be 2,2. That means chlorine will take 1. It's going to look like this. So chlorine and beryllium will share a pair. That means because beryllium has 4 electrons, there is 2 inside. Okay, like the shell will be like 1, 2. So it will be 2,2. Now the whole of the 2 that is outside has been used to form chemical reaction, to form chemical bond. Okay. Now let's now use this idea. According to this thing we see on the screen, it said bond to bond pair have the weakest kind of at repulsion. And I said that again. They said they said the shape of a molecule, according to the electron repulsion theory, they said the molecule will take up the shape that minimizes the repulsion between the electrons. Okay, the shape that minimizes the repulsion between the bonding and the lone pair of electrons. But in this case, we don't have lone pair, so that means they push each other. The two of them that are pushing is the bond pair. So that means bond will push each other and try to maintain as much distance as possible from each other. So it's most likely going to look like this. Okay. So in a nutshell, any compound, I said, any compound that have no lone pair of electron, but two pairs of bond pair is going to be linear. Now this shape is arranged on a straight line, so it's a linear shape. Okay, it's a linear shape because it's arranged on a straight line. So beryllium chloride is a linear structure. I think you understand that now. Barium chloride is a linear structure because there is no bond pair. The shared pair had to push each other farther apart to maintain distance. Okay, that is the first example. Let's try to do the second one. Boron trichloride, for example, boron trichloride. Now, oh, I have to mention something. The other one that was linear, the bond angle between them is one bond. The bond angle between them, since it's linear, is on a straight line. The sum of angle on a straight line is 180, remember? So the bond angle is 180 degrees. Okay, it's very important we know that. Now back to the next one. Boron trichloride. Now let's just draw it anyhow. Boron is 2,3, remember? That means there are just 3 electrons in the outermost shell. And interestingly, all the 3 electrons has been taken by chlorine. So it's going to look more like this. Boron will stay in the middle. Now the 3 bond pair will repel each other equally. The repulsion that is sent by the bond pairs will be equal because there are 3 bond pairs now. This is the first one, this is the second one, this is the third one. So they will repel each other equally. And that means the shape will look something like this. Something like this. So the shape is equally displaced from each other. The shape is equally displaced from each other. And because they are equally displaced from each other, the bond angle between them is 360 divided by 3 because it's equally, so that will be 120 degrees. So the bond angle between them is 120 degrees and the shape is trigonal. Okay, trigonal. I believe I'm making some points there. The shape is trigonal. And the next example is, let's talk about carbon dioxide, CO2. Okay, CO2. Now carbon is 2,4, remember? So that means there are 4 electrons in the outermost shell, and it's going to look like this. Carbon, oxygen is 2,6, so oxygen needs 6 electrons, and oxygen needs 2 electrons to balance, and carbon needs 4. So that means what happens is that each oxygen will take up 2 electrons from the outermost shell. So it's going to look more like this. So if we write it, it's going to be something like this. Something like this. So what I'm trying to say is that in this compound, there is no lone pair again. Everything is shared pair. So the repulsion will still be equal, remember? They'll be equally distributed. And that means that this is still a linear structure. If the oxygen were to be 3, it's going to be trigonal, remember? 3 shape. So you can guess the bond angle here. It's already 180 degrees angle on a straight line. The only thing I would advise is to just master all these things. Master all this shape. Once you master all the shape, it gets easier. If they give you any question in the exam, you can always use one of the knowledge you have. And the next one is CH4. CH4. Methane. Now here there are 4 carbon, and all the 4 carbon will have, remember, carbon is tetrahedral in structure. So normally we do write CH4 like this in structure. On plane is not true. It's not true that this is the shape, because if I drawn it like this, I'm saying the angle between each one is 90 degrees, and you know that the angle in a 3D shape is never 360. When I mean 3D, if I draw something like this, okay, if I draw a shape like this, then this is a 3D shape because I've shown all the possible sides. I show the up, I show the down, the sides. So in this, I'm showing all the direction. So this is a 3D shape. But if I draw only a rectangle, a rectangle. So if I draw only a rectangle, this is a 2D shape. So if I draw this, I've just drawn a two-dimensional shape. But the real shape of CH4 is in three-dimensional form. So most times, you see it in textbook, they'll draw something like this. We draw one carbon, like one hydrogen here. They draw one hydrogen here, and they're going to put something like a broken and increasing line like this. So put hydrogen, and they'll put a strong one here and put hydrogen. Okay, this will be shaded. Now, what this implies that these two happens to be in front. Okay, they're in front of the shape. This one is behind, and this one is somewhere down towards the angle down here. Okay, so it's this one is coming from behind, this one is going away from the front, and this one is strictly on the plane, on the surface. Okay, but to make it easy, we draw it something. You can draw it in different way, but to make it a little understanding, most times you see them drawing it like this. Okay, you see them drawing it like this. So what I'm trying to say in essence is that the difference in such a way that all the bond angle will repel each other equally, remember? So they push each other equally to an angle that is greater than 90 degrees. Okay, it's not 90, no, the angle is greater than 90 degrees. The bond angle is about 109.5, and the shape is tetrahedral. Okay, tetrahedral means four. Okay, four hydrogen arranged. You can also have this in the case of CCl4. Okay, tetrahedral. Okay, and so on and so forth. That's for methane, tetrahedral, and the bond angle is 109.5. So let's talk about ammonia now. Remember, everything we've been treating so far has been the one without any lone pair of electron. Okay, now the one with, what if we have a situation whereby we have a lone electron pair? How do we treat it? That's what we're about to do. Okay, so let's start to look at ammonia. Like I said, ammonia is NH3, remember? So let's try to draw the structure. Normally you see them drawing something like this in textbook. Put hydrogen here, put hydrogen here, then put hydrogen here. Then they'll put two dots on top. Now what the two dots implies is the lone electron pair, the electrons that do not partake in chemical reaction or chemical bonding. So in this case, there is one pair of electron that does not take part, and that one pair of electron is the lone electron, and it's going to make a lot of difference. Remember, I told you the repulsion between the lone, you can see it's underground. Okay, the repulsion between the lone pair and the bond pair is great. It's at least is greater than the bond and bond. Okay, so what I'm trying to say is that the way that these people will fight with each other will be greater than the way that these people will fight with each other. So if this one uses 10 energy to fight, this one might use like 7 energy. So you expect that the fight between these two will be pronounced compared to the one between these, or the one between these. So technically, the fight, the disagreement will push this thing downward. Okay, we'll push this, we'll push this line a little downward, and we'll push this line a little downward towards each other. So the bond here will no longer be 109.5 like in the case of tetrahedron. Will no longer be 109.5 like in the case of tetrahedron, would be around 107. So the bond angle is about 107, and we can say that it's a distorted tetrahedra. So it's not a tetrahedra, it's not really a perfect trigonal. Remember, the trigonal shape is that of boron trichloride. The BCl3 is a perfect trigonal, and remember the perfect trigonal have an angle of 120 degrees in the case of BCl3, But ammonia has an angle of 107, so you definitely know that is not a perfect trigonal. So we can call it a distorted tetrahedron at times. There are other names that may give it, but it's a distorted tetrahedron. I believe that's simple enough. Okay. Now another thing that you might have seen is another shape that we may also talk about is water. Let's talk about water. That one also have lone pair. Okay. Water. Now water is written this way. You would notice, you must have seen it, see them drawing water molecule like this. They say water has V shape. Now, how does that happen? Water, there are two lone pair of electrons, not one. Okay. In the case of ammonia, there is just one. But in this case, there are two. And if you check underground, I said lone pair to lone pair have the strongest. So they are going to push each other. The first thing is the push they will push is so much that they will be so much apart, and they will equally be pushing this. So somehow the water will look like oxygen and folding down hydrogen, because the hydrogen will be folded towards itself. So we can expect that the angle would be smaller than 107, because 107 is the one of ammonia, a distorted tetrahedron with just one lone pair of electrons. But with two lone pair of electrons, I expect a smaller angle. So actually, the angle between them is about 104.5 degrees. So the bond angle is 104.5. The bond angle is 104.5. Okay. So let's try to think about the shapes we have done today. Number one, we started with beryllium chloride. We said it's linear. We went to boron trichloride. We said it's trigonal, and the linear is 180. Remember, we said this one is trigonal, and the angle is 120 degrees. Then we went to carbon CO2. So we said it's linear and it's 180 as well. Then we went to methane, CH4, said it's tetrahedral, and the angle is 109.5. We went to ammonia. We said is a distorted tetrahedron. A distorted tetrahedron is not trigonal and it's not tetrahedron, so it's a distorted one. And the angle is 107, if you recall. I said it will be slightly lower than 109.5. Then went to water. And remember, in ammonia, I said there is one lone electron pair. In water, there are two lone electron pair, and the shape of water is V-shaped. Okay, it's V-shaped, or you say curved shape, or you say chair conformation, but it's better you say V-shaped. And the angle is 104.5 degrees. So all these are the shapes that will represent most of the question you will be coming across in any assessment. So let's use that idea to answer one or two questions here as well. And we're going to also predict from our own basic knowledge. We'll predict the shape of certain molecules ourselves from the little that we have gathered today. Now let's use our knowledge to predict the shapes and the nature of this compound. Tetrachloromethane, I think that one is a very simple one. I mentioned it the other time. It's going to look like this, and the bond angle will be 109.5, so it's going to be tetrahedral. Okay, and just use one of the, so this one looks like the CH4, so you can just use that idea. Once you get a compound that looks like the one you have practiced before, you know most likely they're going to have similar shape. A hydrogen sulfide will look like this. If you look at hydrogen sulfide, it's like you are writing water. And remember, what's the shape of water? It bends, or you use shape. So remember, the water is like this. So it's going to look like you're just replacing this with S and H and H. So it's the same explanation. I don't have to go over the explanation. So the angle between them will be 104.5. Okay, and the shape is V shape or bent shape or whatever you want to call it. So that's fine. Now NF3 looks like PCl3, and it looks like BCl3 if you recall very well. And NF3, you have to be very careful. Nitrogen has 7 electrons, so it's going to look something like this. It's a nitrogen with a lone electron pair. I think there is a lone electron pair there. So nitrogen will have, it has 5, so each one would go with fluorine, fluorine, fluorine. So you're looking at something like ammonia. Okay, remember how ammonia looks like? I told you it's like a distorted tetrahedron. Okay, it's like a distorted tetrahedron. So at times they call it Trigonal Pyramidal. Okay, Trigonal Pyramidal. So what will be the shape of this? It's going to look like this. No, that's not it. It's going to look like that of ammonia exactly. Nitrogen, then with the fluoride being arranged downward, then with the lone electron pair. So it's a distorted pyramid and trigonal. Okay, it's a distorted trigonal, and it's going to look, it's going to be the bond angle I want to say is could be 107. Okay, 107. It's not going to be up to 109.5, or it's not going to be up to 120 because it's a distorted shape. So it's going to look like that. Now the next one is nitrogen monoxide. Okay, you could already predict anytime that you see any compound like this, it's going to be linear. There's no need to stress ourselves about that. So it's going to be nitrogen monoxide. So oxide is 2, so it's going to be double bond oxygen. So it's a linear shape, and the bond angle is 180 degrees. So the next one is aluminum trichloride. Aluminum trichloride will look like you are writing BCl3. Okay, aluminum has 3 outside, so all the 3 are being used for bonding. So it's going to be like aluminum, something like this, something like this. So it's going to be trigonal, and it's going to be trigonal, the Cl, Cl, and Cl, and the bond angle would most likely be 120 degrees. Okay, because it's a perfect trigonal. So it's going to be trigonal pyramidal. But all these are correct. I think that's fine. We've predicted all the shapes. Now there are 1 or 2 things I want you to check out. Now look at this. Okay, look at this. The shapes we've done and the one we've not done, they are all summarized here. Now look, if it's beryllium chloride, like we said, is linear. Carbon dioxide is linear. NO2 is looked like you have water. It's going to be bent. Okay, OCl3 is going to be bent just like water. All those ones are like water. BCl3 is just like the other one that is trigonal. Okay, it's going to be trigonal, but we call it trigonal planar. Okay, so this is not the full name. If you call it planar, it will be wrong. So you have to put triangular. You can say triangular planar. You are still correct. You can say trigonal. Trigonal is a combination of triangle and planar. Okay, so I prefer using trigonal. Trigonal has explained triangular planar. Instead of writing triangular planar, you could just say trigonal in shape. Okay, so they put planar because they expect you to know that it's going to be trigonal, it's going to be triangular, and it's going to be planar. Planar means it's going to be on a flat surface, like a flat. So everything will be on the same line, on the same level, not like it's like a 3-dimension, which one is tilted up, one is tilted down, and like that. That's where planar comes in. But what I want you to see that is the way they calculate the total valence electron. Now, valence electron is the number of electrons in the atomic shell. Now, in this case, we have more than one atom combining together. So in this case, I have, for example, I'm going to use the one that is 24 here as an example, which is BCl3. Now, the BCl3 is boron. Boron, outside the boron is 3. Okay, remember? The valence electron in boron is 3. Okay, plus, okay, you can see that's the 3 into, now there are 3 chlorine, so I'm going to put 3 in bracket instead of writing them one by one. 3 chlorine, each one of them have 7 outside. Okay, that will be 3 times 7. 3 plus 21 is 24. That's how this comes in. Okay, they only calculate the outermost electron shell, and you can also use that to predict. If you already, although it will be a little confusing, that's what I want to teach you, because before you can use that to predict, you must have known a compound that have the same number. Okay, we call it the magic number. Okay, that means you must have known that BCl3 and AlCl3 have the same number. So it's going to stress you. That's why I don't bother. I don't want you to bother with this. I just want to know that there is also a way you can use calculation to predict it. But you must have had the knowledge. All the tests, all the shapes I've taught you. If you can master them, then this number will be useful for you. Okay? Because once you see anything that looks like that number, you can just calculate the number of that one, calculate the number of this one. If they are the same, they'll have the same shape. Okay? We call it magic number. I think that's about the shapes of molecules as well.